Welcome. In this video, we're going to discuss some properties of the definite integral. So suppose, we have these values a less than b less than c. These are along the x-axis, and m is some constant. So these properties will hold. Let's start by drawing some nice axes here. So I have a to b. And what does this tell me? M is a constant, so I know that my m is a graph of a straight line right here. So here's m. And the goal here is to find the area of this rectangle. Well, the area of a rectangle is just the width times the height. My height here is m, and my width, this distance here, is just b minus a. So the value of this integral is just m times b minus a. Let's keep going. All right, so I'm going to draw some function f. Let's say f looks like this. And then I can draw some regions here. I'm just going to, for simplicity's sake, use 4 regions. And now let's sketch in some rectangles with midpoints here. So this is a midpoint rectangle approximately, right there. All right, and here's another one. And then here's another midpoint. And then here's this very tall midpoint. Now what is going on when I multiply this constant on the outside and say I found the area of this rectangle, I'm multiplying this entire rectangle by m, so that rectangle is going to grow. That's going to be the new height of this rectangle. All right, then what's happening here? Well, this one is also multiplied by m, so that's going to grow, as is this one and this one. That'll be the really tall one. So then the function itself, if we trace along these midpoints, our new f is going to look something like this. So we have m f of x. More importantly, what that tells me is that this area can be rewritten as m times the integral from a to b of f of x dx. So I can find the area under this curve and then just multiply that by m, because visually that's what I did here. I started off with these 4 rectangles and then I multiplied them vertically by m. So each of these represents a vertical distance multiplied by m. Let's continue with our properties of integration. So suppose we have these 2 functions. Well, what is this going to look like in the end? What I mean is, if we add these 2 integrals, visually, what will that look like? So let me scooch this over here. So all I did was draw f of x. I kind of resketched it. And now I'm going to go to these rectangles, and I'm going to draw this rectangle, and now I'm going to move it right at the top. And let me do that again. Do you see what I'm doing? I'm just adding these 2 areas together. So I'm taking this area and adding it to make this new taller rectangle. And I'm going to do that for all of these. And that one will go here. And then finally I have one more rectangle left to trace. And this rectangle goes right on top of there. And so this is the area for G here. I should label that more clearly. This is the area for G. And here's the area of F. Symbolically, what this looks like is the integral from a to b of f of x plus g of x dx. So we could find the we could find the area under this curve separately, the area under this curve separately, then add these 2 values together. Or we could just add the 2 functions together algebraically first. So we could add these 2 functions algebraically first, and then find the total area. All right, let's continue even further. So if you notice here, I have this region broken up. So I have this function f, and first I found the area under the curve from a to b. That's what this is. That's the area of just this region here is represented by this first integral. So the second area is represented by this integral. Okay, so here's my sketch, and let me go ahead and sketch in these rectangles. So I'll make these rectangles in blue. And let's go ahead and move them over, and they go from a to b here. And we can do the same thing here for the second part of the function, that is we can just add up whatever area we find under these rectangles and put them together. And if you notice, this is all still just f, right along the top. There we go. So what is that telling you? That is telling you that rather than finding this area separately and this area separately, we can just find the total area together. So now our lower value is a and our upper value is c, so this is the area from a to c of f of x dx. Okay, so let's keep going. So this one is a fairly easy one to sketch. So if this is my function f, and I should just stick to drawing f as brown like I've been doing. So this is f of x. How much area is there in just a line? Well, it's 0. It has a height of a, but a width of 0. So a times 0 is just 0. So the integral of a function where the limits are the same is just equal to 0. All right, on to our last property. So suppose we have the integral from a to b plus b to c f of x, but suppose further that a is equal to c. So what does this become? So I can rewrite this as the integral from a to b f of x dx plus the integral from b to a f of x dx. And based on the previous properties we've discussed, these match up. So I can just use the fact that instead of adding my two areas under the function separately, I can just add them together. So this becomes the integral from a to a f of x dx. And we've already shown that this equals 0. All right, now that we have this long equality written out, let's focus on this part here, the fact that we have this sum of integrals equals to 0. So that is this integral from a to b of f of x dx plus the integral from b to a f of x dx equals 0. All right, so let's manipulate this algebraically. I'm going to subtract the integral from a to b f of x dx from both sides. And what we end up with is the integral from b to a f of x dx equals the negative of the integral from a to b f of x dx. So this is a handy trick if you need to switch your limits of integration. Notice we had b to a, and now we're a to b. You can just put a negative sign in front of it. And visually what this looks like, if you recall, we said a is less than b when we initially started this setup. So if you're integrating in the wrong direction, you can just flip your limits and make that a negative, and suddenly you're going from the smallest to the largest, since you always need to have the smaller lower bound here and the upper bound here. And if for some reason you end up with an integral where the upper bound is on the bottom and the lower bound is on the top, no problem, just switch your limits and make the entire integral negative.